Hello, everybody. Thank you for coming. It's nice to have an audience here. And there may be people joining online, and we're excited that you are here as well. There are several of you online. So thank you for being here as well. Wish you were here with us in person. So we're excited. We're presenting the Youth Engineering Solutions, Designing a Medicine Cooler for Power Outages. Today, you're going to be hearing both a little bit about the program, Youth Engineering Solutions, as well as the specific module that is one of our 6 modules that is coming online for this program. My name is Stacy Klein-Gardner. I work for Youth Engineering Solutions. I'm the Director of Partnerships and the lead engineer for the project. And with me today is my colleague, Andre White. Andre.
Hello, everyone. People here and people online. My name is Andre White. I'm just finishing up my 26th year of teaching. I'm so excited about that. I currently work at Freedom Middle School, where I teach STEM, and I teach 7th and 8th grade there. And for the last year and a little bit into previous year, I got to work with Stacy to pilot this program, and it's been fun. So.
It has been fun. We've enjoyed working together, and I've enjoyed the opportunity to be in his class. So Andre has been one of our 3 pilot teachers nationally for this curriculum, and this particular unit has now gone into field testing and will be published later this summer. But let's get into it a little bit more. So our agenda is we're going to try to really walk you through the curriculum, this particular unit. We have some hands-on activities so you can really try it out and see how it works with the students, with the equipment. Those of you online will probably have to watch and enjoy a little bit that way, but hopefully we can keep you involved as well. So what I wanted to lead off with is, what are some middle school engineering practices? And when we think about an engineering practice, the way I'm defining that is that it's a patterned behavior that leads to the creation of engineering knowledge and products. And I wanted to make a word cloud out of it really quickly. I don't know if people online, you can participate in that as well. If y'all have your phones and want to just use that QR code really fast, what I'm hoping you'll do is to think of, what do you think an engineering practice is for middle school students? So one of the ones I might suggest, and you'll see on mine in a minute, is teamwork. So make it a short phrase. You can enter up to 3 different ones that you want to, but make it short, and we'll see what pops up in our word cloud. If you wouldn't mind switching over to that screen, we'll see what people are entering. So there's 2 I entered to seed the conversation. And let's hope it's still working here. Give y'all a minute to think.
Teamwork is a really good one to use as an example. Lots of teamwork goes on.
At least we hope.
Yes.
All right, let's see. Oh, good, yay, it's working. Hopefully some of these, I've got 2 set of eyes coming up here, so hopefully those of you watching online are participating as well. So some of the ones that y'all are solving, you see collaborations really coming out as a big one that multiple people are suggesting. We've got innovation, teamwork, systems thinking, communication, problem solving, and failure. I love seeing failure up there. So hold that thought. I'm going to kind of walk you through what Youth Engineering Solutions has as some of its fundamentals. Come on in. We'll circle back to this in a minute. If you haven't had a chance to do it, feel free to keep entering more words. Okay, thanks. All right, so can we switch back to the slide deck, please? All right, so YES is a program that actually ranges from kindergarten through 8th grade, elementary, middle school, and out of school. And we are focusing today just on the middle school portion of that. When we think about equity-oriented engineering practices, this is fundamental to doing youth engineering solutions. So we develop students' engineering identity through doing authentic engineering practices, by having socially engaged engineering so that it's relevant and linked to someone, as well as asset-based pedagogies that we use throughout our units. So looking a little bit more specifically at those, socially engaged engineering means that every one of our problems is situated in a real-world context. It introduces multiple perspectives and possible impacts of technology, and it really works on connecting engineering to families, real people, community, and cultures. When we talk about authentic engineering practices, we're thinking about the same engineering design process that I might use as a professional engineer, as a biomedical engineer, but taking it down to the middle school level. So we look at scaffolding those experiences, but we encourage risk-taking and productive failure. In other words, your first design isn't going to work. How are you going to iterate on that? We'll cultivate collaboration and teamwork and ensure that design challenges don't have a single best answer because we want students to design their own one and then see how it works. And lastly, when I talk about asset-based pedagogies, I'm talking about leveraging prior knowledge, developing familiarity with materials, task, and terminology, and creating multimodal, flexible activities. All of that feeds into improving, increasing students' engineering identity and thinking of themselves as an engineer. So I'm going to go back to these engineering practices now. So Youth Engineering Solution has spent some time thinking about what we view as middle school engineering practices. So I think you'll see up here several of the ones that you came up with, probably plus a few others. There were ones around communication, teamwork for sure, persisting through learning and from failure. So a number of the ones you thought of, probably maybe plus a few others that you just didn't have time to think of, but really wanting the students to identify as engineers. I also really want them to think that engineering isn't just a guess and check. It's thinking about the math and the science that is age appropriate and having them apply that math and science into making informed engineering design decisions. All right, that's just a real quick general overview of Youth Engineering Solutions. So what we want to do now is talk a little bit about the specific unit we're going to focus on today. So Andre's going to give us a very quick introduction into this unit.
So basically, when you're looking at the engineering medicine coolers, what we did was we set up a scenario with the kids. The one that I particularly gave my kids is that there's a community you have to identify, and we did some things, and you guys will get to see how that works, but we figured out which communities would benefit best from having medicine coolers that would work to help keep medicines cool and at the temperatures they need to be. Some examples I gave them, we brainstormed and talked about, well, how does medicine get to the pharmacy? And 7th and 8th graders didn't know that. And so we talked about how they are transported from one part of the country to the other, right? And then sometimes train accidents happen, stalls happen, planes get delayed, and if your medicine is not sitting at the proper temperature, what happens to it? Well, we talked about how it gets destroyed. So basically going through this unit, there's 9 lessons that will take them and take you through how to solve those. And those are what is engineering. Lesson 1, lesson 2 is frame the problem. Lesson 3 is investigating insulating materials. Lesson 4, investigate cooling solutions. Lesson 5, brainstorm and plan. 6 is create. 7 is test and evaluate, which they really enjoyed. Lesson 8 is to iterate. And number 9 is to go back and to reflect. And I will say this very quickly. I enjoyed doing this unit. And I'm sure that Stacy and I will talk about it. It depends on how your days are set up. Like for middle school, we're on an A-day, B-day rotation because I'm considered related arts. And so we'll talk about the timing of that, but I will tell you that however much time you spend on it, it is a definite, it's worth the effort and worth you putting everything else kind of on hold to get that in. So, but that's kind of the outline of what we're going to be looking at today.
All right, let's get to it. So first, we want to introduce the problem. And this is a problem statement that we've created, but you could also twist it and take it in a particular direction that maybe you as a teacher does, maybe something local. So if you'll flip to the next slide, we're going to watch a very short video that you can show your students that introduces the problem. So if you would, please.
If you've ever been to a pharmacy, you've probably realized it's a comfortable temperature. Is that for the people shopping? Well, sort of, but it's also for the medicine. It matters what temperature medicine is stored at. Pharmacies use things like heating, cooling, and refrigeration, all powered by electricity. If medicine is at the wrong temperature, it can break down and stop working. But what if you didn't have electricity to keep your medicine at the right temperature? Well, Wole Soboyeho, an engineer and professor at Worcester Polytechnic Institute, faced these very challenges.
So a few years ago, I used to spend part of my time going to teach in Kenya. And I lived in a place called Impala Village, where I discovered the Impala Clinic, which is an amazing clinic that provides medication and vaccines to a community in the Laikipia district of Kenya. So the Laikipia district has within its domains regions of Mount Kenya and many, many roads that are not tarred. And so getting through that district often requires four-wheel drive vehicles, and there's some regions that you can't access even on a four-wheel drive. So people over centuries have developed methods that they use to transport themselves on camels, sometimes on donkeys. And that's how you get through to some of the most remote places of Laikipia. So the challenge was that they would take out medication or vaccines on 30-day treks across the region, and they would try to cool these medication or vaccines with ice packs. And of course, the ice packs melt, and once the ice packs melt, they lose their medication after some time, and the vaccines in places where resources are limited. And they ended up, of course, wanting a better solution to this problem.
Wow, Professor Soboyeho's experience makes me grateful that I live near a pharmacy that can keep my medication at the right temperature. But it also makes me realize that there are situations where I and other people in my community might not be able to keep our medications at the temperatures we need. Can you think of any?
So you can see there that we're tying it in with something that's international in this particular case, but at the end, we're going to start to draw out situations from their own experience in their own lives where keeping medicine at the right temperature might really matter. I think you're going to have to switch that one for me. It's going to play again. Thanks.
If you've ever been to a pharmacy,
Thank you. So one of the things we do is we have them start to build the design challenge over time. We have kind of a setup where we look at the criteria, things that must happen, our constraints, things that can't happen. And we also simultaneously start to think about how are we going to judge if something is successful or not. So over time, the students add to this chart as we start to learn more about the problem. So we would ask them, who is most impacted when hot temperatures damage medications? And to look at that, we have two sets of cards that we have students work in groups. So we're going to ask you to do this as well in just a minute. One is around medications. And so we have them first think about which medications are important. Like why does it matter? Are some more important or valuable than others? And we have a scale for them. So we'll have you set this up too, where you have least important medication on one side and most important on the other. And we ask students to think about how does this medication help people who take it? What happens if they don't take it? And how often does someone need to take it? A similar set of cards that is available looks at who is more exposed to high temperatures where they might have medication that fails. So it could be somebody living with air conditioning, or it could be someone who works outside a lot. And how does that impact how important a medicine cooler might be to them? So again, on this scale, we'll rank least exposed to high temperature and most exposed to high temperature. So in the class, we would have students first do the medicine cards and then do the temperature cards. Andre, which set do you want to do?
Let's do the medicine. And what I found with my kids is, as I was walking around and listening to their conversations, I expected to just see them throw medicine anywhere and everywhere and just not really put a lot of thought into it, right? But then they were talking about, this is for this and this is for that. And then they would ask me questions. So, Mr. White, so if we choose cold medicine, is that like daily cold medicine, so they were asking a lot of really in-depth questions with that. So if you guys could do the same. So we're going to start with
Let's just do the medicine one.
the
Why don't y'all
the
come
medicine
up?
cards.
At home, you'll have to maybe hang with us for a minute. So you end up with the scale of least to most. And then I'm going to hand you the cards. We don't have to do all of them right now. We'll just spend a couple minutes. Maybe each of you can take a stack. And the fun part is, like Andre was saying, is the rich discussion with the students and letting them duke it out as to what they think is more important. So maybe y'all can take the cards you have and put some on here for most and least.
And these cards do range from the very basic medication to the more complex, like if you don't take it, bad things could happen.
So one of the cards she's put down first next to least is aspirin. And then there's vaccines, antibiotics, rescue inhalers, epinephrine, insulin, cold medicine, and seasonal allergy medicine, which if you're doing this in spring, you might find more important. Now, what they're now doing is kind of duking it out a little bit and starting to get some in different order.
I even had one group that asked if they could use a highlighter to highlight some of the words on the cards, and that made a difference for them.
And then similarly, we would then have them come in with these temperature cards. And I'll give you, might as well take a second and let y'all do these. So these are different situations around temperature. So she's just put down living with air conditioning. Those people kind of have the least exposed to high temperatures because they're living with air conditioning. Going over here on the most end, we have living with no air conditioning or living with no electricity as well.
And the overall purpose of the two sets of cards is that once you have them ordered from least to most, then you just kind of look and you come up with a scenario. It's not just one thing. They work together to come up with a scenario to see which people in what situation would need the coolers the most.
And it gives the students really a chance to think about and empathize with why people might need something that they might store at their house in case of an emergency. Maybe it's a power outage that then they can then pull out and put their insulin in. So if they take some of these medicines that have to be kept refrigerated, even having a hurricane come through becomes a big deal in some of these areas.
And then again, you also want to gauge their thinking. So I'm going to ask you guys, what did you choose as your least important medication and why? Pain relievers. Okay, they chose pain relievers, and why would you say that's the least important?
You don't always necessarily need them, and a lot of times it's just to increase your comfort, not a life or death situation.
Not a life or death situation, and you don't always need them. Very good. Same thing. What did you choose as your most important and why?
There are two there for me that are very equally, epinephrine and insulin. In both cases, you can die. You can have an acute reaction and die as a result of it. So you do use insulin every day. You use epinephrine intermittently, but in both cases, both can result in acute death.
And that's the kind of conversations, that you want to engage. So if you didn't hear that, to those of you that are online, epinephrine and insulin was their kind of most important. And again, it's because of the benefits of it. And those two, if you don't have them, it could lead to death or just other severe type things. So again, what you want to do is you want to engage them in these conversations before you throw it out there.
Thank you
Good job,
for
guys.
participating
Thank you.
in that. Obviously, that would take longer in the classroom. And I want to mention, one of the things we talk about in Youth Engineering Solutions is that this is an engineering and computational thinking curriculum. So you're starting to see the engineering as we work our way through the engineering design process, but we also have activities that are powered by MathWorks, who is our funder for this particular project, and using in the background, we're running MATLAB code. Now the students don't have to see that, they can click a button and see the code, but we do a little bit with them to dive even deeper into engaging and understanding the problem by looking at temperature data and where heat waves have taken place in the United States, and so they're accessing large data sets to look at that. All right, moving forward, we might have in our classroom updated and added to our criteria and thinking about what we want our design to do, and then thinking about how it might be successful. So moving forward, again, we're skipping forward a little bit for time's sake. Lesson 3, Andre, let me click through these slides for you, and maybe you can explain to them our testing station setup. We've got sample materials that we can show them, and then what the ultimate point of lesson 3 is.
So what we wanted to do with lesson 3 is we wanted to get into the actual testing to see what insulators would make the best medicine coolers, right? I think it's important that you do highlight the vocabulary before you start. So, and then our first one is the heat. And the kids knowing that energy is transferred from a warmer system to a cooler system, with that explanation being to them, and also because when they think of cooler, they think that we want to keep things inside. We want to keep it either hot or cold, because now you've got the warm coolers as well. And so, but we want to kind of isolate that and have them remember that we're talking about keeping medicines at room temperature and colder. So the next thing, Stacy, you want to get to, so where you want to?
Well, I was just going to hold up. You want to tell them about the station? I'll hold up the parts, and then you could tell them what materials they test.
So in the stations, so what we do then is once they have their box that's going to become their medicine cooler, they have different insulators that they can put in it. So some of the ones that we let them choose from are felt. They get to choose that. We've got bubble wrap. We've got aluminum foil. We've got cardboard, and we've got foam. And another good thing is just I would brainstorm with them and just say, okay, before we talk about anything, who thinks that this would make the best insulator? And I'm pointing out to the cardboard, and we talk about why. So that was just always something good to talk about before we actually got into the testing. Going further into that, over at the station, the testing stations, we have a light. And you have a thermometer, you have a timer.
That's all for now.
And then so we'll talk more about that in a few minutes.
So we test each team tests a different material, and they'll test one piece of it, and then they might test 2 pieces of it to see if more is better or not.
And when she's saying pieces, we're really talking about layers.
Yeah.
So we'll do 1 layer, and then we'll test it, take all the data, and then we will put in a second layer of the same insulation.
So ultimately, after we collect all this data, the data is shared amongst the class. So I'll share my felt data with you if you give me your bubble wrap data. And we ask the students, once they have all of this data, to put on another one of these things, move these pieces around to say which materials are the best in their opinion. What does the data show make the best insulators?
But they are the ones to use their data to go through and make that decision on which one is the best insulator.
So keeping on going here, if now we're asking them a guiding question of how can we lower the starting temperature of the cooler? So we introduce
what I call our magical formula, potassium chloride. And it's kind of neat. That's what's inside. That's the main ingredient inside of ice packs. I hate to kind of admit it. I didn't know what it was called until we actually did that.
So they just do a brief testing of using different amounts of potassium chloride with the same amount of water, and they measure the temperature drop. And they actually hold it because you can feel it get cold. And they come to find out what are some optimal values of how much potassium chloride to use? Because it turns out it caps out, after about 7 grams. So they discover all of that through this investigation.
And going back to keep up with, what we're doing in STEM, the math part is they have to come up and they have to measure their potassium chloride. And a lot of times we got to show them how to use a scale.
Yep.
And we'll say to them, so if this was 3 grams, let's guesstimate what you think 6 is going to be. How much do you need to put in the spoon to try to get it? Because I made them go right to the exact measurement, and some of them got frustrated with that.
They did. So then we start to talk about how do we combine these two things? How do we combine the cardboard box, which is the cooler, with its insulating layers of whatever materials they choose, with also having something that is cold inside? How do we put those two things together in order to make our best medicine cooler? So we move forward with that a little bit. We have them start brainstorming. We start to introduce cost as a variable. So you can have 2 different size boxes. You can have more layers of different materials. They all have cost. And eventually they find out that they can't have everything they want. So they have to make good choices about which materials they want to use. Moving forward again, they brainstorm, they fill their budget, we approve it, they get to buy their materials and build their medicine cooler, and then eventually they're to the point where we test and evaluate. And that's where Andre and I want to pick up with you today and actually let you do the testing. So what we've brought today are actually 3 different, actually there are like 10 of them. I saved all of the students' medicine coolers from when we did the pilot test. So you're using his actual students' medicine coolers. And what we're going to ask you to do is to do some of the testing today. We're not going to do all of the tests because there's some tests around like how many bottles fit in it, but we are going to look at temperature. So I'm going to give you a copy of this sheet here in just a second, as well as the evaluation sheet, so you can see what those look like. And, oh yeah, I'm missing that slide. Okay, great. So what you're going to do, you want to explain what they're going to do over here? Yeah, why don't you come up to the station? Come on up, everybody. I don't know if we can we bring the camera up?
We'll probably just do one station.
Yeah, let's just do one.
So to save time, I've already measured the potassium chloride for you. We've got 3 grams of potassium chloride in here. So what you're going to do is, and we'll just use this medicine cooler, you're going to put about 30 milliliters of water in this, which is about that much. Then you're going to pour the potassium chloride in. You're going to shake it for approximately 30 seconds. Fill it before you start shaking it. Fill it after you start shaking it and see the difference. Now, what we would typically use in a classroom is a glass beaker. And so I don't know how this is going to be, but this is the actual medicine cooler or medicine thing that would go in there. But you can try it and see. So again, the process is go ahead and pour your 3 grams in of potassium chloride in, then put a little bit of the water in, and then fill it. Actually, you know what? Let's do this. Let's do the water first, right?
Sure, and then we'll put.
So I'm gonna let one of you guys hold that.
Yeah,
let's just do it. There we go. Teamwork. So here we go.
Teamwork makes it.
We're trying to do this on the fly. So we're going to do 6 grams. So let's change it to 6 grams. So where's your cup at? There's the cup.
Yeah, we can each pour them in. We'll get more.
Okay.
We'll get more to drop.
So go ahead and put a little bit of water in.
Yeah.
That's good. That's
all right. You're good.
Let me see how much is in
Maybe
there.
a little more than that.
A little bit more, yeah.
Sorry, Stephanie. We set you up.
That's good. That's
Okay.
good.
All right.
You want to let everybody?
Here.
Want to let everybody fill the cup before,
Yeah.
or you just want to do it? It doesn't matter.
Oh, yeah. You might touch it. Here, I'm gonna let. All right. Can you do both? And then. All right. So, it's potassium chloride. They're both potassium chloride. I just decided to put more in.
So everybody just kind of passed the bottle around the medicine little tablet container around.
Maybe put the
now,
lid on.
you're going to put the lid on.
And let's shake
now, shake it for 30 seconds approximately.
Tell us if you feel anything or observe anything. Okay.
All right. So then now let everybody grab a hold of that.
Here, let me just stand there and hold that. Okay. I just grabbed one of the kids, so then I'll let y'all do it.
And
Close
so
it up.
for those of you at home, what they're using, their cooler, they actually have a combination of aluminum foil and felt. So this group did 1 layer of each. Now they did get the data from each layer before they put them together.
All right, so then we have thermometers, little small thermometers with, let's open it back up and let's drop it in here. And then you can close it back up. And then we can turn this on.
Now, Stacy, you want to put one on top, or we're not going to worry about that?
Let's not worry about it for now.
So what we typically did in the classroom is we would use, if you guys want to come over here, we'll just make it real life.
Yeah.
We'll put a light over it, and if one of you will hold the light, hold it for about, oh, there you go. And so, there you go. We typically, we put a thermometer on top of the box and one inside the box because we were constantly getting both temperatures, the inside temperature as well as the outside temperature. And you hold the light over it for about a minute, and then you take that data.
All right, and then we've got a timer, or you can use watches. So you take a minute. So temperature inside the cooler, what is the temperature now?
Started at 19.3, it's at 19.9 now.
Okay, here, shall I be your scribe? Sure. Okay.
And actually what we
Right.
did,
stole your
Stacy,
pen.
is we would do it at five or six different intervals. So we would take a temperature at a minute, 2 minutes, 3 minutes, all the way up.
So we're gonna take a few minutes and take some data here. So the one thing you can do with group work is like there are lots of jobs to be had here. Everyone's got their hands on. They're all busy doing something, and they also get to chit chat a little, which they like while they're doing it.
Now, they were really, and as we were assigning the jobs, they were really, and then that's another thing, you assign the jobs to the kids to make sure everyone has one so that everybody has the buy-in. And again, even with middle school, they really, took their jobs that they had pretty serious.
All right, 1 minute. What's
19.5.
19.5? All right, let's keep going. We budgeted time for this.
So what was the 1 minute?
1 minute was 19.5, so it's kind of...
Room temperature was the first one was 19.3,
Or
then
19.9, you said?
19.5.
Yeah,
Now it's 19.
it's already down to 19.
Now it dropped to 18.9.
Oh, good. And we haven't even gotten to our 2-minute mark. We'll go for a couple more. On the sheets that we have, like it's a nice data sheet. It's got a place for a data table, and then it also has a place for them to graph their data at the bottom. One other thing we do, and I won't show it to you today, but you even get spreadsheets from us where you can collect their data and plot it using a Google Sheet. We did Delta T, and we had we ended up plotting all the groups on what graph. And so the kids could look at it and say, well, my graph was in the middle. We're like, which graph do you wish you were? And you could go find out, do a little espionage with what that group did. 2 minutes.
You got to remember, I think we started off with the one group having 3 grams of potassium chloride, and I think we went all the way up to 10 or 11 grams.
Yeah, 10 was the max.
10. And then when you left, we had a few more do a tad bit more than that.
Did they discover it didn't matter?
It didn't matter.
Yeah, it definitely has an exponential plateau there on it.
Is it you?
No, it's not me. I'm not feeling it that much.
I do smell
Like
it,
a
yeah.
rubber.
It's like burnt cardboard smell.
They're saying it's a burnt cardboard smell. We see no flames or smoke.
Observations.
Other observations.
That didn't happen in my classroom either.
All right, we're getting close.
That smell.
And 3 minutes?
19 even.
19, that's interesting. What-
It's been going back and forth between 18.7 and 19, like within
Yeah.
seconds of each other.
But I will say my hand may go up and down.
Well,
so
and
there
so-
might be air in our.
So one thing Stephanie's, one thing they're both noticing is that their hands might be moving a little. So in the classroom, we have them set the boxes like on the floor or on the table so it's not moving. And then similarly, the lamp is at a fixed height. And you can actually usually tape these to a chair or something like that and be about a foot over.
And for those of you online, most of the lamps that we're using, they have clamps on them.
Mm-hmm.
So, had the kids clamp them to a table or something.
Holding steady at 19 now.
That's weird. That's why it's not dropping more. So it's not dropping a whole lot more. Let's see, we're about to be at the 4-minute mark, which we might cap our data collection there. We could also try a different cooler if we have time today. and see if somebody else's cooler does better at getting, what's the temp?
19.
Still at 19. So they really haven't, you might stop, they haven't really seen a lot of decrease in temperature, but maybe that's because they didn't.
The bottom feels cold.
The bottom feels cold, Stephanie's noting.
My hand's been underneath that.
Yeah, you've been holding it from under there. It's interesting.
Well, you got to remember too that the potassium chloride is in there.
Right.
And that had gotten kind of cold.
So it could be that means it's not a good insulated box, right? Like if you can feel through it, that means it's not doing a great job. Thank you for letting me borrow your pen without asking. Oh, that's, okay, yeah, well, I think we're all going to step out at 2:30. Gotcha. So we can maybe try some more if we have time, but for sake of time, it's a lot of rich time for students to graph and to think about their graphing, what goes on what axis, why does it go there, what does the data tell us? Like who had a good, successful medicine cooler and who didn't? And then, of course, if you flip over to your handout that you have here, there's an evaluate page on the back. And so they can take their data and we kind of help them think through how to think about whether something was good or not. And again, we're assessing things other than just temperature. It also includes like how many medicine bottles can it hold? Is the cost at the right price point? And what will you change? So we actually help them think through what do they want to change and how might the cooler's performance in other areas change if that area improves. So asking them to do that and then letting them test again. I know one of the things that's easy to do in an engineering class is to go, okay, this is what you do, great, let's finish up because you feel like you're out of time. But that next stage is crucial because that's where they start to get more success. And that's representative of the engineering design process. All right, and Andre, anything else you want to say about maybe let me do this and then I'll just let you kind of talk a little bit more about your experiences with it, if that's okay.
Yeah.
So we have 2 units that will be published for free in late summer. One of them is this medicine coolers unit, which is great for a STEM classroom as well as a science classroom that uses energy heat transfer as one of the scientific topics. It's a great way to tie in your engineering design into the science. We also have a unit coming out called Eco-Friendly Slippers, which looks at like recyclable materials and things like that, materials choice, fast fashion, and combining that with a study of conservation of energy and friction. We have 2 more units that are in pilot testing right now, one around landing pads. So if you think about Amazon in the future might be delivering via drone, well, you need something at your house to catch those packages so that it doesn't just go plop and break it. So you're designing a landing pad for that. And lastly, we're looking at vision extenders and if you're a bike rider maybe, how can you extend your vision and see more and stay safer? So those units are all coming, plus 2 more that I can't even tell you about yet. But they're all going to be for free. And you can find them at youthengineeringsolutions.org is where they will land later this summer. So let me pause there, and I just want to turn the floor over to you for a minute, Andre. Our email addresses are here if you want to follow up with either of us about anything. But Andre, maybe talk a little bit more about your experience.
I think the best, and what sticks out to me more than anything is the engagement that my kids had. It's hard, even in a STEM class, to get the attention of 7th and 8th graders. But throughout these lessons, the engagement was so high. They were talking about what is happening, why it's happening. That was one benefit, just to get them up and moving. I was on this for a while because, again, we're A day, B day, so I see them every other day. But I was able to get 8, 10 grades, and I did this with both 7th and 8th grade. I was a little overzealous when I first started, and I was going to do it with all 8 of my classes. Then I decided we need to cut it way back down just because of the materials and things. And speaking of that, the kids had part of the fun for them and enjoyment was cutting out their own materials. So again, that was an experience, hearing them talk and share some of the stories about the medications that they've been around, the medications that some of them even take. I'm like, whoa, that's a little bit too much information. But anyway, it was there. They were able to talk about that. It's just a really, really fascinating unit. There was never a boring day, and I think you definitely should do that in your classroom. The engagement and everything is it's awesome.
It was fun. I was in his class for all of it, so it was great to hear about
It
it.
was a different story every day.
Yes, there was. Let me see if there are any questions either in the room or any questions online, because John is back there dutifully moderating that. There is not, and that is just because we have not fully published. Like, it's coming this summer, and when it does, there'll be all of the teacher guide, the teacher's PowerPoint, the engineering notebook for the students. All of that will be freely available. So you're kind of catching us as we're finishing up the editing and getting it just right. But youthenginieringsolutions.org is where you'll be able to find it.
And just the copies that I was provided, that they gave to me, they were very organized, very easy to follow. So I'm assuming that the update would be even better.
Yeah, and when he told us they weren't, we fixed it. So, do y'all have any questions in the room? It's okay if you don't.
So I love that you're having them collect data and then you're having them kind of graph it. Have you considered allowing them to think about how they might want to display that data? Like, as they think about data visualization, from a computer science thought here, right? As a standard to kind of looking into computer science standards, the new ones will be all, there is a data analysis, I think, and part of what we want students to be able to do is how should you display data?
Right.
Right? And like, I know we guide them first, but I was kind of thinking, I look at this, I think, oh, I wonder if students would come up with different ways of showing their data.
So the question is, do we want to allow the students to do the data analysis themselves and to think about what data would they plot? How would they plot it? What kind of plot would they make? Absolutely. I think it depends a lot on what age your students are, how much they've done before, and how much time you want to spend on it. So there are definitely instructional moves to be made as an individual teacher with an individual class to take that however you want to. You could do it by hand, which is kind of what we have them sketching out here, or maybe it's time to go get on and use Google Sheets and have them think about how they plot it and how does it look on the screen, what's the scale of the graph. All of those things are absolutely up to the teacher's discretion.
Yeah.
Any other questions from the online? All right. Well, why don't we wrap up for here, and it's an official ending, but if you have any questions, feel free to stick around or to message either one of us if you think of something else you'd like to know. Thank you for coming.
Thank you.